right? So we are concerned with this drying of concrete. We know that there's no diffusion down here, so there's a flat gradient, and out here, water is diffusing into the air. We know air has some non-zero concentration of water. So there may come a point where enough water has exited the slab that actually the air starts to contribute water into the slab again. So it might well be the case that the slab is dry enough that the air is actually causing water to diffuse back into the slab. So that all implies to us, right? If there's water leaving here and there's water coming back in, that implies to us that we can reach an equilibrium or a steady state. So that's something we should always take a few minutes to think about. Is steady state even possible here? And yes, if there is a restoring action and if there is a consuming action, then yes, it's possible to get to a steady state. And so towards that, when we look at the balance that we did last time, let's look here. So in chapter 2, we had developed in this section 2.4, we had developed the material balance for concrete. So this is what we had. This B should be subscript here, of course, right? So we have this equation, and we are saying now that this can have a steady state. So at steady state, of course, dx dt is a 0, leaving us with this on the side. So I have developed the solution here in chapter 4, but let's just do it together. So let's just open up a Word document so we can talk through it properly. Okay, so we have this balance. So we know it's at steady state, so we can set the accumulation to 0. And we've got DAB, and it's DDY. So we chose Y to be the vertical direction. And then it's DDY off, and it's NA, which we know is D is 1 over XA, right? So if you go back and look at this balance, it's 1 over 1 minus XA, dXA dy. 1 over 1 minus XA, dXA dy. Oop. 1 over XA, so yeah, 1 over 1 minus XA, dXA dy. So this is the balance that we have. And of course, it's equal to 0 here, so we can divide out this diffusivity. So that's the equation that applies at steady state. So that's what we need to solve. And if we look at this, number one, we can just integrate this with respect to y. So we can say here, y, or not y, we can say k1. So the constant k1 equals. And so integrating on this side, we are just left with the kernel in here. So 1 over 1 minus XA. And we've got left here dXA dy. Okay, so after the first integration, that's what we have. And then, sorry, this should be y. And then here, we can see, we can separate the variables. So we can take the dy there and integrate dxa over 1 minus xa. So we've got k1y, k1 dy equals dxa over 1 minus xa. And now the variables are separated, and we can look at integrating this. So on this side, of course, we have a k1y. So we can say here k1y plus k2. So there'll be a new constant of integration there. Oops. And on this side, we can write it as a ln of 1 minus xa. And then it's a chain rule, so we should say minus here. And when you do an integration, you can always just check. So if you differentiate this right-hand side, so it's the derivative of a ln, so that means you'll get 1 over 1 minus xa, which we know we have. And then you have to differentiate within that function as well. So the derivative of 1 minus xa with respect to xa is a minus 1. So minus 1 times 1 over 1 minus xa, then that's the same as that. So we can see this is the integral of this function. So that's the general solution that we have. And of course, it's got these two constants of integration. And we're going to use the boundary conditions to evaluate those constants. Just to pause there, any questions or comments so far? Okay, so let's first state those boundary conditions. Well, we did do it last time. 1 second. So last time we said that at the base, it's an insulation type of boundary condition. So our BC1 was that NA there was equal to 0. So we had NA at y equals 0 equals 0. And NA, if we recall, the molar flux expression was, it was this one, right? So this is what we have for the molar flux. And so if we're saying NA equals 0, so this part equals 0. Just a second, I just want to check. Yeah, so if NA equals 0, I just don't want to lose a solution here. If you apply the 0, you can easily lose a solution unnecessarily. But okay, if NA equals 0, let's take it that dxa dy is a 0. So NA equals 0. That implies to us that dxa dy equals 0. And now if we look here, right, we've got this, remember after the first integration, we have this equation. So just going back to where we integrated our original material balance, we'll just copy this down here. And we want to translate this boundary condition. We want to apply what we learned in this boundary condition. And we should be a bit specific here. Let's just say here, this is true only at y equals 0. Y equals 0. So that's the boundary condition as we expressed it last time. Now we've taken our first integral, and what we'll do here is multiply both sides by 1 minus xa. So just copying this, Control X. And we can say here, at y equals 0, dxa dy equals 0. So we can express that here as k1 times 1 minus xa at y equals 0. So the mole fraction right at the base, that's equal to 0 here. And this helps us in giving us an expression for K1. Well, the K1 actually vanishes here. So it's not that helpful. So yeah, we can't actually separate a K1 in this case. But what it does give us is that, let's see, at that, it gives us that that's a 1. So y equals 0 is a 1. So that's interesting. For some reason, it says that the mole fraction of water, there's a 1, which is not really possible. So there's some issue here that I'm not seeing. Let's see, so at this point, so the first integral, K1, that's what we have, and then just separate the variables. It all looks fine, K1y, then that's fine. And here, this boundary condition, we are trying to make use of this boundary condition. So at y equals 0, the flux is 0. Here, the flux is 0. So the gradient is 0, which we said last time. And now we want to try and use this. And so, well, I guess the way to read this now is that there are two possibilities here, right? For this gradient to be 0, it's one of two things. One is that this part is a 0. So if this is 0, then that means ya at the base is a 1. And we know this is not possible. It can't be the case that the mole fraction right at the base is pure water. We know that's not true. So we reject that solution, and the only other solution is that K1 is a 1. So that's how we make use of our boundary condition. We can use it to obtain our constants of integration. So we can say here K1 equals 0. And then if we look at our balance here, it tells us that K2 equals this. So K2 equals, K2 equals minus ln of 1 minus XA. Now, we have the other boundary condition, right? So number one, we found K1 is a 0. Now we still need to find K2 if we want to use this solution. So the other boundary condition we have is that at the surface, we have a known mole fraction. And what we actually wrote was that the concentration just inside the concrete, so we said this as the concentration at the position y equals h minus, that's equal to the equilibrium constant multiplied with the saturation concentration. So we said in air, there's a certain saturation level of water in that air. So that's our other condition. And of course, both these concentrations are, well, not this one. Let's see, this one is in air. This concentration we can rewrite as a total concentration and a mole fraction. So we can say here that this equation, we can say here this equation can be rewritten in terms of a total concentration times a mole fraction. So total concentration times the mole fraction is equal to this. And of course, we can just divide through by that C. So that's using our boundary conditions so far. And we'll just write this as the X. And we'll divide through here by this C. So this C, of course, is the total concentration in the concrete, right? So that's regarded as a known constant. And Ca sat, that's the air concentration, which is also something we can look up. So there are tables that tell us the saturation concentration of water in air under different conditions. So it depends on the pressure and so on. But just taking standard temperatures and pressures, let's say there's a fixed value of the saturation concentration in air. And then in the problem, we are given Ke. So everything on the right-hand side is considered known. So the part that's left over is we want to apply this in our general equation here. So we can say K2 equals, and now we've got 1 minus XA. So this XA, if we just apply y equals h minus, well, there's no y on in this equation. So we can just say this must be true at the surface as well, where x equals this. So if it's true at this one point, it must always be true for all points. And so we now have we now have an expression for K2, right? This unknown constant, we have now related it to the physics of the problem. So if you go back to the general solution that we observed, right? If you look at the solution we obtained here, right? This is our general solution. We found K1 was 0, and we now have an expression for K2. And so we have found finally what our conversion is at steady state. And in fact, if we apply this, let's look at what XA is. And let's see whether this makes sense. So we've got K2. So we know K1 is 0. So this part can vanish. And then K2 is equal to all this. And now we've got minus log on both sides. So we can say all this is the same as, right? So if those two are the same, that means their arguments must be the same. So on both sides, we have 1 minus x. So we have 1 minus xa here. And we have 1 minus ke. See, I sat over that. And then you've got 1 minus in both cases. So if we subtract the 1 from both sides, this is what we have. So this equation is telling us that the mole fraction of water in the concrete is eventually, right, at steady state, that mole fraction is going to be the saturation concentration adjusted for concrete. It's going to be the concrete equivalent of the air's saturation concentration, right? And it's a constant. You can see it's not a function of y anywhere. So it's telling us that eventually our solution is going to be this, right? And I'm saying eventually because it's the steady state solution. And we know that we are going through various intermediate steps. So initially we start out with a 10%, I think it's a 10% concentration of water. Then we said we start losing water on the inside. So we start losing water, and as we lose water, we start losing it at the upper surface here. So we start losing water from out here, and then water is progressively lost until we reach a stage where all the concrete is completely equilibrated with the air out here. And in fact, we should expect this result. We didn't need to go through this whole exercise. We could have gone straight to this. Why is that? Any proposals there? See, how do I find you here? Anyone want to answer why should we expect this result? When we said out here that we expect steady state, we imposed the condition of steady state here. Then we did all this development and we found something. And now I'm saying we should have expected this in the first place. Could we have just gone ahead and written this down? Any hands up for yes? Any hands for no? Okay, no one wants to commit. Okay, well, You see, we have to eventually equilibrate with the air. The only way for this concrete to be at steady state in terms of its water content is that we know that in the air, we'll have a certain concentration, and it's going to be a lower concentration, we know, because it's a gas, right? So if we have the air concentration here, and let's just give it a different. So we've got the air concentration of water here. Then if you multiply by the equilibrium constant, you'll get a certain concrete concentration of water, and that's at equilibrium. The only way for us to have steady state here is if all interior points are at the same value. In other words, there's no net flux here, and we are in perfect equilibrium with the air. If both those conditions were not met, if we didn't have a flat gradient here, then there would still be water diffusing around the slab, and so we would still not be at steady state, because water still on balance moving from one location to another means that your concentrations are changing in time. So the only way to have a steady state, number one, is for us to have a flat profile here. And number two, the value of that flat profile, the concentration at all these points, must be the equilibrium concentration. If it wasn't the equilibrium concentration, then near the surface, the concentration will have been changing, and then that would drive flux in this direction. So this is the one steady state that's possible under these conditions. Any questions or comments there? Okay, so towards developing a more general solution for the concrete, we know at least this is eventually where the concrete is going to end up. And it's not the final answer that we are looking for. We want to know when the concrete has a 1% content of water. Now, this is going to be less than 1%, right? And that's something you can test, but that is less than 1%. This is a lot more than 1%. So the time when we do reach 1% is somewhere in between. It's something like this. So this confirms for us that we do need the unsteady state solution across this whole space. Okay, and if you're wondering, well, how do I know this is that this adds up to the 1%? Right. Number one, we can do a balance here. I'm sorry, I just want to stop my phone connecting and disturbing this. Okay, just a second. Okay, so that the 1%, we expect it's at some intermediate time. So we need a way to count up the number of moles that are in the slab. So what we want is that the mole fraction in the whole slab is 10%, not 10%, 1%. So what we want to say is that the total mole fraction, let's write it like this. XA bar, right? So XA bar is equal to 0.011%. And XA bar, we are going to say is the average mole fraction across the whole space. So to get the average mole fraction, we can get the total amount of water in the whole volume and divide it by the total number of moles in that volume. So we can say the total number of moles of water, let's just write it symbolically first. So the total number of moles of water in the slab, let's just define that to be Na, like that. And then the total number of moles, let's just call that Nt. So that includes the concrete, the silica, the ceramic, whatever that constitutes that concrete. And we can recognize that this is in effect the concentration Ca times the volume. And similarly, we can see that Nt is going to be the total concentration C times the volume. So it looks like that. So we can see that Ca over C, right? So that's the ratio that we are looking for. We want to say that 0.01. So the way to estimate the number of moles of A in the concrete is to integrate the number of moles if we look vertically through the slab. So if we take, let's say, a differential slice here. So let's just pick a different color for this. So if we pick a differential slice here, then we can pick at position Y, between position Y and Y plus delta Y, there's a certain number of moles of water in the slab. So we can say here DNA, and this we did see before. When we were doing the material balance, we did define the finite volume there. We said that we have a delta. That we have a delta NA, and that was equal to the concentration at that point. So the concentration at position Y times delta Y. And what we want now is NA total. So we want NA, the total number of moles in the slab. And we can, of course, get that by integrating all the contributions across that slab. So we can say here, sum over I, and it's delta NA I, or we can write that as the integral of dNA, right? NA is, of course, the integral dNA. And we can also write that as the integral of Ca with respect to Y if we multiply that by the cross-sectional area, which we know is LW. So think about that. This is the concentration at position Y. And then if we are taking a delta Y, and then multiplying by LW, that's effectively multiplying by the volume. So this effectively is how we add up the number of moles of A in the slab. And we have to do it that way because it's not necessary to do it here. The concentration is the same with respect to Y. Also, initially, you don't need to do it because, again, the concentration is the same. But it seems that the time when the concentration is not flat is the profile that we need. So in a profile like this, where the concentration is varying with Y, the only way for us to add up the number of moles is by doing this. So we are looking for the time when Na is equal to, or Na over N is equal to 0.01. So let's write that as our criterion. So Na over N equals 0.01, and that's equal to this entire integral. So now we have our criteria. Well, here we need to divide by the total number of moles as well. So divided by N. So that's our criterion. So what we can do also is acknowledge that the concentration profile is generally a time function. So Ca is a function of T and Y. And so we seek the time at which this statement becomes true. So this is our criterion. It's not always true, right? In other words, we are looking for the time when this becomes true. So now we have our criterion for answering this question. We know that once we get the solution CA as a function of t and y, we can integrate it at each instant in time. So we integrate it with respect to y for each instant in time, and we check to see when that is equal to this value. And then that will be the time when we reach that, and hence that's the time when we classify that concrete as being dry. Okay, any questions or comments there? So far, we have introduced this idea of using our boundary conditions to find things like the constants of integration. So in the next step, we'll want to solve this differential equation. Here's where I'm not completely sure which way to go, because you actually haven't reached the maths that you need. In your maths classes, you haven't reached this solution of second order ODEs, as far as I know. So, and we're not really out to teach what's going to come up in maths later on. So I think the best way to do it is just to give you the solution to the second order, the second order ODE, the solution to that, and then we can just use that to answer the question. Can I ask, in your maths class, have you done solution to the second order ODEs as yet? Thumbs up if you've done solving the second order ODEs. Okay, so I'll take that to mean we haven't done the second order ODEs. So I'll just provide the analytical solution to that, and then we'll use that to answer this question next time. Okay, but that's how we start to solve these problems. We first look for the extreme cases. We look at something like a steady state. How does the solution behave? Then start looking, develop our criterion, and then looking at with the time solution, when does that criterion become true? So this is the type of thing we do when we are solving these sorts of equations. So that's the first one. Then, of course, we also have the cylindrical geometry. And let's go back and look at what we had in that case. So for cylindrical geometry, we had, right, so flow in cylindrical geometry. This was the equation that we had. So let's look at a slightly simpler version of this. Sorry, there's a question on the chat. First, about uploading on Learn instead of YouTube. What I found is that when I upload on Learn, number one, the video disappears after a while, and then then when people want it much later, then they can't get it. And then I think people are used to just referencing that playlist anyway. So that's why I prefer to just upload to YouTube. You have a kind of permanent access to it. Then what is H minus? So just going back to the drawing, I guess. Yeah, so and I've said this a couple of times, that our height here is H, right? If I just sketch this, the height of the slab is H. But when we are pointing to an interface, right, we have to think of this as our interface, because above here, you've got air, and down here you've got water, you've got concrete. So this is an interface separating air and water, and we are saying that the height is H. So when we are trying to write something about the concentration, then we can't talk about the interface. We can't reference just y equals h, because let's say I write it like this. Let's say I write CA. So if I write here CA at y equals h, then the question becomes, then it's, what do I mean here? Because do I mean the air or do I mean the concrete? So Ca, that's of course the concentration of water. We know that we have water in the air and we have water in the concrete. And those are very different phases. In the air, the density is much lower. In the concrete, the density is much higher. So we know those concentrations are different. And we have referenced the interface here. So we don't know which phase we are talking about. We don't know whether we are talking about water in air or water in concrete. So to get around that, we can think about which one is at H plus. So when we say H plus, that means a value that's higher than the interface. So we are talking about looking above the interface. When we say H minus, then that's looking below the interface into the concrete. So H plus is referring to the concentration of air in the concentration of water in the air, and Ca at H minus is the concentration of water in the concrete. Okay, so it's just a way for us to specify where we are looking. So that's why we need that. Does that cover it there? Let me just check the chat again. Okay, thanks. Okay, any other questions or comments there? So, yeah, I wanted to cover that today as well, but do it as an exercise and we'll talk about it tomorrow because we're out of time now. But look at the cylindrical flow example and take the case of steady state and deposition on the wall. So, okay, let's list it here. So we want to know about, let's see. So what we want to look at next time is cylindrical coordinates flow in a pipeline under conditions. Number one, that it's steady state. Number two, that it's turbulent. So it's radially well mixed. And I think that's it, right? So under these conditions, can you apply the boundary conditions and find a solution as we did today? Right, so that would be the next one. And you can see we are applying some assumptions here. So of course, in the next round, we'll go ahead and relax those as well. But under these conditions, can you find a solution as we did today? Right, so please start thinking about that, working on that, and then we'll talk about it further tomorrow. Any other questions or comments? Okay, if not, that's it. Okay, 1 second. Okay, so about submitting your answers. Okay, I'll have a look at the difficulties in submitting those, and then we'll figure out a way. Yeah, if we have to, we can just do paper submissions. That's also fine. We'll work out how to do that. All right, then I guess that's it for today. See you tomorrow.